So today I want to talk about challenges and opportunity in mobile manipulation, of which we have done a lot of work recently, and I'm very excited about it. And of course, as you are probably aware, the majority of manipulation research is still done in tabletop scenarios like these ones, right? Like these are some examples from our work, but fill in whatever other thing you have seen on social media recently. It's basically mostly done in this way. And of course, that is very constraining in the sense of what tasks you can actually do. And so if you have a mobile robot, you can actually go out there and go beyond these very constraining and maybe a little bit boring tabletop tasks and actually bring robots into your home and pick up guitars if you let your robot do this, or actually fill the laundry machine or the dryer and things like that. So that's where we really want to go, because I think that's where the scene understanding methods that are coming from this community are actually really becoming super valuable. But of course, if you bring a robot into the real world with all its messiness, you will discover some challenges. And I want to show you 3 challenges right now. I'm sure there are many more, but let's start with these 3. So first of all, let me ask, just to get an idea, who here has worked with real robots before? Okay, not too bad. So maybe like a third. Okay, so all of the people who just raised their hand, they understand the pain of working with a real robot, right? And all of you have never worked with a real robot, you have no idea, right? Like you're just looking at Twitter and LinkedIn and whatever else you're following, and you're seeing these cool humanoid demos, but you haven't seen the pain of the engineers and of the people who collect the data to actually make that work, okay? And so, of course, we are facing that in our research because we're trying to bring all these methods and all these learning methods and whatever onto messy robots that are sometimes really just research prototypes. Rarely can we buy things off the shelf. So this is just one example of our mobile platform that we actually happened to get donated from Google X. And we refurbished it completely, and it was done by, grad students from mechanical engineering in this case. And you see the wiring looks, a little complicated, let's put it like that. And it's actually very brittle, just as you would probably expect from looking at this wiring. And so reliability of hardware is a huge problem. So that's certainly a challenge if you want to move around robots into actual real world scenes. And then, of course, if you have a mobile robot, you have way more degrees of freedom. So in this case, we just have one arm on a mobile platform. So we added 3 degrees of freedom, position and orientation. And what happens now is that this suddenly makes teleoperation, which is one of the main ways to collect data these days, way harder, of course, because you have to control more degrees of freedom. And of course, also it makes it harder to learn. You have to think about the action space that you're actually outputting with your policy, which has suddenly grown in dimension. And so I love to work with mobile robots like this. That's like complex enough for me. Of course, everyone is excited about humanoids right now as well. But think about the level of added complexity that you have there, right? Like these humanoids, like for example, the ones from Tesla that I show you in this image, have like 20+ degrees of freedom. And so the people who are collecting data for them, like the ones you see here in this image, they, if you look at the ad, they are asking for people who are fit enough to walk for 7+ hours, and they have to carry 30 pounds of equipment with them, right? So think about that. If you go out in the real world and you do mobile manipulation, that's what you have to deal with. And then, of course, maybe the exciting part is actually that you get this increased level of diversity, which is great, but it also means you somehow have to get more data to actually cover this diversity of the space, right? And that's certainly really hard to do when you have to do that on a real robot. Okay, so today I want to talk a little bit about how we are addressing these challenges in my lab. And let's start with hardware, actually. So this particular platform that you see here kind of open, we actually used it for a really fun project that was called TidyBot. Maybe you heard about it before. And that robot just does what you think it does. It cleans up, and specifically it cleans up your place according to user preferences. So the idea is that this robot is deployed into your home, And then you, as a user, of course, have a very specific way how you organize your apartment and your home. And we want you to be able to just go to the robot and tell it, like, here are like 2-3 examples of where things go in my place. And then we use an LLM to actually go from these examples and generalize from them, summarize them basically to get more generalized placement rules so that the robot can actually deal with objects that you haven't actually exactly provided a preference for. So that's kind of what we did. And then we had this system build up that would actually do this household cleanup. And this was really exciting to I call them normal people who are not like, roboticists, and especially parents of small children were like the most excited about this. And also the children were very excited about it, who we presented this to, because they could make a mess and then the robot would go and clean up after them, which they loved. And so we did a bunch of real world evaluations. So here's just an idea of the objects that we used in my lab in this case, and the receptacles that were actually there for the robot to place stuff in. And then Jimmy, who's the first of this, would just, set up our experiments right like this, really fun. And then the robot would basically do things like this, right? So you see on the top left there, you see the predicted category of the objects, where it's going, and then whether it's throwing stuff or picking and placing stuff, okay? So yeah, so isn't that cool? Don't you want that at home? I kind of want it at home. Yeah, so that was our project. How do we do the whole perception? I didn't even talk about that. We used, in this case, we kind of did a few hacks because we only have 24 hours a day. We had like ceiling placed cameras that would actually use object detection from there, and then we used like open vocabulary object detection and clip to just like categorize these objects, first from the camera that was on the ceiling, and then from the camera that was actually on the robot and pointing forward. It's not so important, but it worked really well. And so here's like one thing that happened. So when we released this project, suddenly I received at least one email every week from fellow researchers who were like, where did you get this base from? So everyone was excited about the base, this mobile base, because it's holonomic, which I will explain in a second why this is exciting to people. The important thing is you cannot buy it because, as I told you, we were super lucky. We got it donated from Google X because they weren't using it. And we just refurbished it, so you can't buy it actually from the market. But people really wanted it. They were going to pay whatever. So Jimmy and I, we were thinking, like, what if we built an open source, low cost version of this platform? That, like, given the emails that I'm receiving like every day, that will probably have a lot of impact. And so that's what we did. Here's one version, and here are all the other versions with like different robots. Like, it's like super flexible platform that you can customize according to whatever arm you have. It can be an expensive arm, it can be a cheap arm, whatever you have, and you can spec the battery and the size of the frame as well. And so coming back to this point that the reason why this platform caught so much attention is because it's holonomic. So what does that mean? It basically means that this platform can move instantaneously in any direction, so it can translate and rotate simultaneously. It's like if you think about your office chair that has casters, it's basically like that. It's a motorized office chair. It has the same caster mechanism, and it's different from the more common differential drive that most mobile bases have, which basically is like a car, right? Like a car is not holonomic, and that's why you have to do the three-way park or whatever the thing that's called, during parallel parking. Okay, so why is this cool? That it just moves like in any direction instantaneously. It's cool because teleoperation becomes easier. So here's an example for a task where this really makes a difference. Teleoperation becomes easier. You see, like on the right side, you have this robot really maneuvering around. It's like super awkward. Teleoperation is easier and learning is easier, right? Because with this data that you collect with the non-holonomic robot, the data is also kind of messy and annoying. And so basically your policy has to implicitly learn all the weird constraints that are existing with a non-holonomic robot. So also Jimmy made something really cool. He made like an easy teleoperation interface using a phone. And he basically uses this phone to control either the base or the arm. And it runs on my phone as well, which was honestly surprising to me that it just worked. But I could do that as well. And then the cool thing about the robot is, and this interface is, you can literally kind of just walk next to it with your phone and walk the robot like a dog almost on an invisible leash. And do interesting mobile manipulation tasks in your home. And so here are some more examples of what Jimmy did in his apartment, where he actually built this robot. And you see how, for example, in the middle, in one of the cells, you see the robot cleaning the bathtub, and it really has to squeeze in into this narrow space, right, like between the toilet and the bathtub. And you know, you can't do that if you have a non-holonomic robot. And so it's really versatile, it's very cool. And of course, now that we can collect demonstrations, we can also train policies. So in this case, this is just for, you know, for demonstration. We trained the diffusion policy for all of these tasks, so these are autonomous. Okay, so one thing you might say, given all the humanoids craze out there, is like, but the stairs and all the terrain, blah, blah, blah. Well, it turns out wheels get you really far, even on rugged terrain, right? Like, so here's just Jimmy's robot on Stanford campus, outside of the Gates building. And, you know, it's switching between different kinds of floor really seamlessly. It doesn't matter if it's carpet or not, or if it's some kind of weird construction, you know, surface or whatever. And it has a lot of payload, right? Like, this is Jimmy driving himself over some really annoying terrain, and it's working. So this is also different for you might have seen like other holonomic or omnidirectional robots that have like these wheels with the tiny parts, with the tiny wheels on it. Those are really annoying because they get dirty, right? So you can't really do that thing. Our robot just has casters, which are way more robust. So yeah, we published this robot, this whole thing, open source and all, and price and whatever, at Coral last year. So this is the paper, and then Jimmy did this insanely detailed documentation. If you print it out, it's like 200 pages or something like that. It's kind of crazy, but it's very detailed on how you build your robot. And so one thing that is really cool that I'm really proud of is that actually people start adopting TidyBot outside of our labs. So we have a bunch of labs at Stanford, but also this is a video from Princeton who reproduced it there. Meta has a robot. A bunch of startups did like other versions of the platform. So this is Hexfellow, who Jimmy has been like in touch with, and they built this version of it. And then we have just people doing it for personal use. So this was really cool. Nat Friedman, who used to be, if you don't know him, he used to be the CEO of GitHub, and he founded GNOME. So he's a huge proponent of open source. And he, out of the blue, sent Jimmy this video of him using this robot, actually, which was really cool. And then it's also being used for art. So this is a version of TidyBot of this platform, basically modified by Katie Kwan during her artist in residence position in the SF, in the San Francisco Exploratorium. And they built this platform, and then they built a hand around it. And so you see the hand here kind of behind these dancers. And there's like a whole show, which I also haven't been able to see yet, but today is the opening night. So if you're happening to be back in San Francisco by 6 p.m., you could see it. I know I'm also not back by 6 p.m., but anyway. So that's really exciting to me, and it shows that, oh, this is actually really indeed very useful. So, so that addresses our hardware problem, okay? Because that thing that we built, first of all, it's cheaper, and it has very few parts. It doesn't require soldering, so even if something breaks, it's super easy to fix it as well, even for undergrads. So that's very exciting, and I hope maybe some of you get inspired and use that platform to do mobile manipulation research that actually exploit the kind of scene understanding methods that you're working on. Okay, so let's talk about second problem, tele-op. Because of the more degrees of freedom of these robots, right, like tele-op is harder, but also learning becomes harder. So let's talk about this. So, right, like we want to bring our robots out in the world and do all these fantastic tasks. But I also showed you earlier that Jimmy had made this phone app, but here the arm and the base are still decoupled from each other, right? Like, so he has to Even though it's sort of simple, he still on the phone has to kind of switch between what he actually controls, even for this. And so in one of our recent works that was just released on arXiv, actually, Priya here, who led this project, developed basically an even easier version to teleoperate this robot, still with a phone. So here what she did is she basically implemented a whole body controller on this robot, same robot as you see as our initial prototype. And she also implemented self-collision. So you see, like with her phone, she's actually only controlling the position of the end effector, so of the hand. And she's trying to make it collide with itself, to basically drive into the base. But since it's a whole body controller and it tries to do collision avoidance, the base is actually moving backward to get away from this hand, okay? So basically now you don't have to switch anymore. You just control the position and orientation of the end effector, and the base moves gracefully with it, okay? So, and this is how she brought this robot to her home. So all of these things are done in her home. You know, we did these are autonomous policies that were learned from her actually using this teleoperation device for some of these tasks. Again, these are diffusion policies. So they are not actually side comment exploiting the kinds of methods that your community is actually developing. This is basically a method which I will explain in a bit, but it essentially takes like either full images as input or point clouds that are not labeled semantically, right? Like, so it could be interesting to combine this, but I'll talk more about the methods in a second. Okay, so now we address the teleop problem for these robots, right? Like we have basically this cool phone interface, and now let's come to the third problem, which is you have more diversity in the task and in the environments and objects and so on, but now you also got to cover all that space with data somehow. And so let's talk about this method that Priya developed to actually let the robot work on all of these diverse tasks in her home. And so what Homer is the name of this method. It's basically a hybrid policy that is connected to a whole body controller. So hybrid is a hybrid policy because it has two arms, basically, or two legs, or whatever you want to call it. But basically, this policy takes as input some observations and a mode. So what are these two modes, or the previous modes, right? Like, the modes can either be a key pose policy, which is basically some position of the end effector in space, or it could be a dense policy that is basically predicting end effector deltas, so basically changes to the current end effector pose. And both of these are used for different use cases while you're actually manipulating. So let's look at this one first. So the key pose policy, which basically predicts some pose in space, is good for long range reaching, right? Like for the arm actually going somewhere roughly into the right space. That's easy to do for roboticists, right? Like we know exactly how to then get to that pose once we have the goal pose. We have all these motion planning methods, so we could just use that. And so what this part of the policy actually takes as input is a point cloud. Again, remember, this is segmented, the point cloud. Actually, is it segmented? It's not even segmented. And it doesn't use, it doesn't use any of the fancy semantic scene understanding methods that you're using. But that's what you're using here as input, a point cloud. And then the policy is actually predicting an absolute end effector pose of the robot. So the way this works actually under the hood is that the point cloud is labeled with a saliency value essentially. So in this case, it's a bit hard to see, but basically this point cloud is from the shelf, like the TV shelf thing, whatever it's called, with the knob as for the draw. And so basically the salient point will, if the method works well, be on that knob for opening the drawer. And then the key pose policy basically also predicts a relative pose of the end effector relative to that salient point. So in this case, relative to the knob. Then this policy also predicts the next mode. So should it predict another key pose? Or should it go to the dense policy, which I explain in a bit? And it also predicts gripper action, which is in our case just open or closing. Okay. Okay, so that's the key pose policy, one of the arms of this hybrid policy. What's the other arm? That's the dense policy. And that one we basically use for fine-grained manipulation. Okay, so that's when you finally kind of roughly got there close to the knob for opening the drawer, but now you need to actually more precisely align the end effector with that knob to get there. And so what does that take as input? That one takes 3 images as input. So in this case of this robot, we have a camera on the base that is kind of like on a camera stand, right? Then there's another camera on the base that is kind of like on the mobile base and actually looking forward. And then there's a wrist camera on the arm. So we take all of these images and some kind of end effector pose, so proprioception of the robot, put that as input to the dense policy, which by the way is a diffusion policy, and then that predicts the next mode. So should it redo the dense policy or go back to the key pose policy? It predicts gripper actions, so open and close, and it importantly predicts the relative end effector pose as well. Okay, so now given all this output, we pick basically the next end effector pose. That one is sent to the whole body controller, which now actually takes care of the entire robot, including the base. Okay. So as you can imagine, that's really useful for navigation, for example, right? Like, so you can like really predict far into, as far as your depth camera sees, basically, right? Like, which I guess is around 6 meters or something like that. And really just go there, do collision avoidance on the way, all of that kind of stuff that we actually know how to do very well. Okay, so we compared this method with a bunch of baselines. So in this case, the first 2 rows here are basically vanilla diffusion policy, which is basically just some imitation learning architecture. It's not important what it is, that predicts every time step a delta action of the end effector or of the base as well. So in the first row, we actually still decouple the base and the arm. In the second row, we use the whole body controller. And then Homer also doesn't use the whole body controller, but outputs in a larger dimension action space and also tries to control the base at the same time. Okay, and so what we find in these 6 tasks that we did here, simulation and real world, basically Homer is outperforming the next best baseline, which is Homer, with that doesn't use a whole body controller by like 30%. And so here's like a more detailed breakdown for each of these tasks according to these baselines basically. And you see like a quite a significant difference here. And the reason why diffusion policy, for example, doesn't work very well is because it has to deal with 20 demos only per task. So that's one of the goals here, actually, right? Like to deal with this diversity in mobile manipulation. We want to actually, we need more data, which we can now do with our simple teleoperation setup, but also we want to have better policy architectures, right? Like that maybe don't need as much data. And so that's what we achieved here by connecting this hybrid controller with a whole body, with a hybrid policy with a whole body controller. Okay, so then we did something on top of this. You remember maybe that I mentioned that the key pose policy arm is predicting a salient point on the point cloud. And so as another way we thought about where we can maybe use VLMs is, what if we provide the salient point from the outside? So in this case, we used MolMol, which is one of these vision language models that is good at pointing at things. And so we use that point on the point cloud as a way to condition the hybrid policy. And then, of course, MolMol is like very good at generalizing over different appearances and shapes, variations, and so on. And so we did have some initial experiments where we show that we can change this hybrid policy to also take VLM input as well, and then generalize much better. So here are some results on this where, especially if you go into out-of-distribution scenarios, conditioning actually on points that are provided by a VLM is actually very promising. All right, so so I hope this showed you a little bit of how we deal with this diversity by just having smarter policy architectures, essentially, and maybe plugging in VLMs that do not need robot data. They are actually trained on data that's independent of robotics, actually collecting data on a real robot. We are doing a lot of work on smarter policy architectures. So one is, for example, that I'm not going to talk about in detail today, where we actually embed equivariance into a policy architecture. So this is a particular example where we take a diffusion policy and combine it with vector neurons, and therefore the policy can actually generalize to different position orientations and scales and appearances as well, because it uses actually a point cloud as input. So what is cool about it is that now we can actually use demonstrations by a person. So here on the top row, on like random little, how's it called, like napkins or, like small tissues and stuff like this over small boxes. And then we can use these demonstrations that are actually provided by a person on like miniature version of maybe the task that the robot has to do to train these robot policies. And here in this case, they're even executed by, by two robots that are collaborating. And so for Equibot, we have all of these different tasks, again, that are only learned from human demonstrations, and they generalize to different variations of the same objects. In variations, I mean position, orientation, and scale. And of course, appearance, because we use just point clouds. And so what is cool about it is that works really well. So at the Stanford Robotics Center opening that happened in November, we ran Equibot for like 3 straight days. There's even a cameo, so you see if you can spot Fei Li, she's also there with her kid, one of her kids. And one fun thing that happened is like this couple there in the top right, they were like, can we, we did this whole demonstration without people in the beginning, and then they were like, hey, can we get tucked in by the robot? And we were like, yeah. So the robot's never seen people actually sitting on the bed, right? So they had to deal with that kind of variation. And it worked pretty well. And then everyone just wanted to be tucked in by the robot. And so that's what we did all day. So that was really cool. And it was 3 straight days of autonomous demos where we were still fighting with the unreliability of the robots. But anyway, so this was Equibot. And the cool thing is for teleoperation, instead of teleoperation, we can actually now use demos from a person as well, which is so much easier to collect than if you have an actual robot in the loop, right? And then maybe the last work that I want to show, and I know I only have 4 minutes left, I just want to quickly show you this work. This is also a solution to deal with the problem of the diversity and sheer scale that you suddenly have to deal with if you bring robots out into the wild, right? So here we considered the problem that we call the policy mobilization problem. So let's say you have an image-based policy trained from fixed or limited camera poses for a task like grabbing these paper towels, okay? So we are interested in running this policy on a mobile platform where the robot is initialized at a random pose and needs to navigate before running the policy. And naively navigating towards these paper towels and executing the policy may actually result in an out-of-distribution initialization of this policy, leading to failure. So here, for example, on the left, the robot gets too close and pushes actually the towels inward with the arm, or on the right, the orientation of the robot actually makes it hard for the left arm to reach the paper towels. So one thing you can do is you could just improve the robustness of this policy by collecting more data from all of these different situations. But that, of course, is annoying because you have to collect more data, like now in a potentially huge space. So to handle this, we actually defined this new problem of policy mobilization, which aims to find the optimal robot pose that leads to an in-distribution viewpoint for executing the policy. And here's just a brief overview of how this works. This approach consists, the approach that we are proposing consists of 3 key components. So we have a Gaussian splatting model that a robot could just like figure out by just being deployed to your home and just going around your apartment once and creating this Gaussian splat for rendering then the scene for a hypothesized new viewpoint. And then we have a hybrid score function for estimating how likely a policy will be successful when executed from a given viewpoint. And so there we assume we have access to the training data that the robot actually had to learn a policy. So then we compare a hypothesized view with like these training data points using CLIP. We have a detector that basically says, oh, is the object of interest according to my language instructions actually in view. And we also do some collision checking as well. And then given the score function, we use Bayesian optimization for iteratively optimizing robot position and viewpoint. And in this work, we assume the camera is fixed relative to the robot base. And this means that if you sample a robot pose, you automatically determine the camera viewpoint as well. And here's some real robot tasks that we evaluate on against two baselines. And you see this is basically done in a grocery store. So here's our method that needs to, where the robot basically needs to grasp and extract a bag of chips from the shelf. And this method basically navigates to this appropriate base position and successfully completes the task. Here's like a stupid baseline that's just behavior cloning with more data actually. And it's typically out of distribution and just goes to random places. And then we have actually a smart baseline, which is smart because it's done by a human. So this person who is basically moving the robot is being asked to move the robot to a place to pick up the chips. But the person doesn't know anything about the policy. It just picks like an intuitively good position that should be good for the robot. But even then, because the policy has been trained from a particular position, this often fails as well, right? Like because intuition doesn't match within distribution of the policy that was trained in. Okay, so here again are some the other tasks where the human baseline actually works, and we have this poor tomato task as well, and so on and so forth. I know I'm out of time. Here's like something cool we can do. We can also now chain the same policy together in a much larger space to, for example, close out drawers. We can also generalize to new layouts. And we can do something in a very big space as well. So this is like in a whole mock grocery store setup, actually at TRI. And then here you see the optimization process. And then the robot basically drives to this position that is in distribution with respect to the policy, actually. This robot is also interesting because it has like this additional degree of freedom of actually moving up and down its torso. And so we can, of course, optimize over that as well. Okay, so this is one method that we did. It's like the first one that we propose as a baseline. If you think you can do better than us, which I'm sure you can, you should try it in this MobiPy framework, which actually has metrics, baselines, visualization tools. It's based on Robocasa. You can train the robot on many different versions of kitchens so that it actually generalizes. So yeah, check out the paper. It's on archive since a few days. And so, yeah, these were the three challenges I wanted to cover that, you encounter when you actually do mobile manipulation with MobiPy. And I hope you can, find that inspiring. Maybe you also get one of these robots and then go beyond tabletop tasks where you can actually use the open scene understanding methods that you're all developing. My personal vision is to go towards collaborative mobile manipulation. Humanoids are cool and whatever, but I actually think if you have like a fleet of simple robots like this with like a single arm and they can flexibly team up or not, do things either together or asynchronously, that would be really cool. I think kind of way better than humanoids. I don't know. You fight me on that. Okay, so thank you for your attention and thank you again for the invitation.
Do we have any questions? I think we got time for one or two questions.
Wow, everyone is flattened. Okay. Yeah.
So we have a microphone here in the front. You can just come up and.
Hey, great talk. Thank you. So I have a question about sort of what your thoughts are on robot morphology. So you had all Jaco arms in these examples, or it looks like Jaco.
Gen 3. Yeah, Kinova Gen 3.
Yeah, but like, so what if you replace the arm on the base with like a UR5 or something that's now like you have singularities in the joint space and all that, like would your like sort of vision of the future be you're just training like a new whole body controller for every morphology, or is there like some more flexible, more general purpose.
Okay, cool thing about whole body control, we already know how to do it. Like, and literally the same whole body controller that we use on that robot with the Gen 3 Kinova arm, so it's like the one there in the middle, will work out of the box on all of these other robots that you see here, right? Like, we don't need to learn that stuff. It's done. There's like, so that's the first one. It already generalizes. It's not based on learning. That's why it generalizes actually, without collecting more data. But the morphology, here's another interesting thing about if you were to put this your 5 arm, let's say, which you also did, it's just not in the pictures, what happens, right? Like, so you say it has a different kinematics and different singularities and all of these things. So first of all, with the whole body controller, we can just take it and like put it to that new one. But the second thing is, because you put it on a mobile base, you now added 3 more degrees of freedom. And that means that you increase the degrees of freedom and you actually have a bigger null space, meaning you can do things in that null space while keeping, for example, the end effector in the same place, but basically moving the rest of your body around, right? And so therefore, you can actually avoid all these weird singularities because you have a lot of null space dimension in which you can do alternative things to running into a singularity, for example. Yeah.
Yeah, awesome. Thank you.
Thanks. Okay.
In the homework setup, you mentioned that you were using the Malmo VLM, and so I was curious to know, one, why did you choose that instead of maybe doing some object detector for your key point analysis, and then maybe two, if you could talk to the VLM people and ask them to give you like the magic perfect VLM, what would that look like for you?
Okay, cool. Yeah, okay, first question, why did we use Malmo? So that one was just like very easy to integrate with our current architecture, which is relying on salient points in the point cloud, right? So it's literally like one 3D point of that point cloud, and then relative to that one, we predict the 60 pose of the end effector to go to. And so you could use an object detector as well, we just haven't tried it. It was just more easy, like it was like a smaller step to go. But it could be interesting to do an object detector as well. We just haven't tried it. Okay, what would I want from a VLM? Spatial and physical understanding that is better. And things that actually Francis showed as well. He's, by the way, also co-author of Homer. He like having like mechanisms, right? Like the articulation mechanisms of all of these different things that are in homes, like doors, drawers, and so on, right? Like prismatic and revolute joints that are there. I would love to know that, right? And then often when we have that kind of high-level understanding from a VLM, we can actually use a lot of what we know in robotics to deal with it from there, right? Yeah.
Thank you.
Okay, I think I'm out of time, and maybe the next speaker. Thank you.